All right, so we got a Garfield cartoon to start us off. Looking at tomorrow's weather, the high temperature will be between 40 below zero and 200 above. And Garfield's like, man, this guy's never wrong. Do you feel like that weather forecast was very useful?
Yeah.
No.
Damn.
Probably not. Now, different question. Do you feel like the meteorologist got it right?
Yeah.
Oh yeah, for sure. He should be very confident in his prediction, but it's not very useful. What he has given is a confidence interval. He has given an interval of values that could be possibly the truth about the weather, but it's not very useful. We, as statisticians, hope to create intervals that estimate the true value, but that they're useful. So we have to balance out how useful is it and how confident do we want to be that we got it right. But before we continue with confidence intervals, we need to review. What is the notation for sample mean?
X bar.
X bar. What is the notation for sample proportion?
P with the hat on.
P hat. All right, cool. Tell me the notations for your population parameters.
Party P.
P.
Party P.
There's three most common ones that we use.
U.
P, sigma, and mu. All right, cool. What is the sample statistic that goes with P?
Standard deviation.
What?
Huh?
What sample statistic estimates P? P hat. What sample statistic estimates sigma? What sample statistic estimates mu? Okay, cool. We are going to continue using these notations and continue using these population parameters. Just like we did in chapter 7, we're going to focus on proportions and means. Okay? All right, so since we're going to continue focusing on proportion and means, let's just review. The sampling distribution of P hat. Does anyone remember the mean of P hat? What is the mean of P hat? It's just P. And where did you get P from?
The problem.
The problem. It told you what it was. All right. I know you don't have a formula chart in front of you, but does anyone happen to remember the standard deviation of P hat?
It's
Okay, cool. And does anyone remember what we had to do when we find the standard deviation? There was like a condition we had to check.
10%.
Yeah. So we have to check the 10% condition. Does anyone remember what the 10% condition
Make sure
is?
the thing is 10 is less than or equal to 10%.
Good. 10 times the sample size has to be less than the population size. Okay. Basically, the sample has to be 1/10 of the population. Again, I will tell you more about that in 8.2 when we do 8.2. But for now, we still have to check it. All right, cool. And then when we're working with sampling distributions of P hats, how do I ensure that the distribution is approximately normal?
Central limit theorem. CLT central limit. Yeah, if it's a
The large count condition. If the large count condition is met, can you please remind me what the large count condition is?
NP is greater than
That's the
greater than or equal to 10.
No way.
N1
So
minus P is greater than or equal to 10.
Perfect. And then usually at this point, we would be asked to find some sort of probability that another sample of the same size was a certain thing. Okay, cool, great. Fantastic. Normal CDF, life is good. So that was what we did for proportions. Now let's review sampling distributions for means. What is the mean of the sampling distribution of X bar? It's just equal to mu. And where did you get that mu? It was told you in the problem. Does anyone remember the standard deviation of X bar?
Standard deviation
It was the standard deviation of the population, which was given to you in the problem, divided by the square root of the sample size, which was told you in the problem. And what did you have to make sure you checked? I'm sorry, for the standard deviation. You still had to check the 10% condition. That was still a thing. So 10 times n had to be less than the population. Now, what did we do to ensure that the sampling distribution of X bar was approximately normal?
Either the CLT central limit theorem,
Or it's already said that the
or
proportion is,
if the function was said to be the original one, the sample, the population was approximately normal.
I feel like you just started throwing out words there, Danny. Or the population is approximately normal. All right, so look, for a mean distribution, an X bar sampling distribution, either my population is approximately normal, and it said so when I read the problem, kind of like that Phineas and Ferb monkey problem that was on your free response test last week. It said that the distribution of monkeys was approximately normal. So that was great. You just had to, there it was. Population was approximately normal. Life is good. If, however, it doesn't tell you the shape, or it tells you that it's right skewed or left skewed or bimodal or something like that, then as long as your sample size is bigger than 30, then CLT applies. What does CLT stand for?
Central limit theorem.
Very good. Do you guys remember all that fun stuff? Yep. Now, here's the good news. You guys did not learn all of that for nothing. We're going to keep using it. Sort of. Here's why, sort of. There's a really big difference between Chapter 7 and Chapter 8. Are you ready to know what it is?
Just go in your watch history. Just go in your history. Oh, he can't go there. He cannot go there.
We will no longer be given the parameters. Wait, what?
What?
We are no longer going to be given the parameters. What did I just tell you you're no longer going to get? You're no longer going to get P, mu, or sigma in the problem. So how are you supposed to use the formulas that we just wrote down when you're not given the data in the problem anymore?
Very carefully.
That's what we are going to figure out in this unit. Because in the real world, you don't know the true value of the population. So, you're no longer going to get that anymore. I have a little activity for you.
Oh no, Miss Like,
Turn the lights on. Whoa.
I have a jar that has beads in it. There are some blue, there are some red. I will bring it around to your group in just a second. And I want you guys to give your best guess for the proportion or percent of red beads in this jar. You're not guessing how many beads are in the jar. You're guessing what proportion are red in this jar. Do you understand what you're going to do? All right, I'm going to bring it around and let everybody look at it. All right, so everybody has had a chance to look at the jar. What I want you guys to do is write down. Write down your best guess for what proportion of red beads are in the jar. You're going to write it right here on this blank on your notes.
46.9.
You can write it as a percent or you can write it as a decimal. It doesn't matter.
Wait, so what's the actual?
So this is the best guess, okay? Now, realistically speaking, how confident are you that you have just guessed the exact proportion of red beads that are in this jar?
About 50%.
Write down how confident you are in your guess that you have just guessed the exact value proportion in this jar.
I think I'm about on the fence on all these.
All right, so how confident are you guys that you have just gotten the exact guess? 50%? 0%, 3%, 5%. These are some of your feelings about how confident you are. You're not very confident, it sounds like.
You know why I'm not confident? Because I guessed 100%.
Just
Oh,
like
well,
you put me
there
down for 100%.
All right, now, here's what I'm going to do. Because I know you tried really hard to get close, I'm going to give you an interval of 10%. So what you're going to do is take your best guess, whatever your best guess is, and do 5% on either side and create an interval of a guess. Mine, for example, if my guess is 50%, my interval would be 45% to 55%. You are basically taking your best guess and adding 5 and subtracting 5 in order to get an interval of possible true values. Now, everybody has a 10% window of options for the true proportion that are in the jar. And now, how confident are you that your 10% window includes the true value
100%.
that is in the jar?
65.
Okay, maybe now you're up to 65%. Maybe you're at 47% confident. Maybe you're at 50% now. I don't know.
You doubt yourself.
But do you all agree? Do you all agree that you're more confident now because you have a bigger option here? Unless you're Danny and you know, okay. All right, cool. All right, here's what I'm going to do. I want you guys to increase your interval to a 30% interval. That means 15% in either direction of your best guess. 15% of your best guess in either direction of your best guess. For example, mine would now be 35% to 65%. Now, you guys all have a 30% window. Shh. You now have a 30% window. That's a pretty big window. The true value could be anywhere in that 30%. But now how confident are you that you have truly captured the real proportion of red beads that are in here?
100% sure. No doubt in my mind.
So maybe you're feeling really good about this and you think I totally got it at this point. Maybe you're like, you know what, 95%. I mean, I'm pretty sure, but I'm not going to say I'm 100%. Maybe you're still not quite sure. So that would be your guess. And then finally, give an interval within 60%. So that is 30% in either direction. 30% in either direction. Now look, for my guess of 50%, I now am saying that I think there's somewhere between 20% and 80% in here. How confident should I be? Well, I'm probably pretty dang confident about that.
At this point, we're probably ridiculous numbers.
Yeah, at this
Not
point,
even guessing
your
it.
interval is really wide, and you're pretty good chance that you're going to be capturing the true value at this point. So maybe you're at like 95% or 98%, or maybe you are at 100%. Shh. Here's what I need you guys to recognize. As the interval widened, as the interval widens, the confidence level, what did it do?
It went up.
Increases.
That is a symbiotic relationship.
As you guys were able to have a bigger window of guess, your confidence that you have actually gotten the real value should have gotten better. You had more options to be right. You had a 10% chance of being right, then a 20% chance of being right, then a 30%, then a 60%. So you had a better chance to be right. So as your interval gets wider, you should be more confident. But wait.
Wait a minute.
Look at that last guess that you have. That 30 or that 60% window. How accurate is your guess?
Real inaccurate.
I mean, if it's very important for me to know what percent are red in here, then how good is this guess right here?
It's pretty
Do you know how much is in there?
I do.
What is it?
Oh, wait. Time out. I don't know if you caught what I said at the beginning of class. We no longer get to know the true parameters.
Well, I kill myself.
So we no longer get to know what P really is.
Tell you what, Jeff,
No,
that takes
it's
one more
not.
time. I'm open up the book.
Oh, but we don't get to know that anymore.
Well, you know what the answer is. That's it. Why don't you just let us know?
That's about as useful as a stair.
So do we know the answer to this question, Mrs.
Don't make
Lake?
no kid.
It's a
I do.
I feel like she's capping.
2023.
No.
Makes that year capping.
Because we no longer get to know the truth.
That's about as useful as capping.
We have two new phrases that we need to make sure we can differentiate between. We have a point estimator, T-O-R, and a point estimate, A-T-E. Okay? How do you know which one is which? Here you go. The point estimator is the statistic used to estimate the parameter. Now, you guys are already familiar with these. What statistic do I use to estimate P?
Oh, we're making me forget.
P hat estimates P. What statistic do I use to estimate mu?
You do the X bar.
X bar estimates mu. And what statistic do we use to estimate sigma?
S of X.
S sub x estimates sigma. So you guys, when I am asking you guys to tell me what the point estimator, T-O-R, is, I am literally just asking you for one of these notations. Once I ask you for the point estimate, A-T-E, this is the value of the point estimator. This is now the value. This is the actual number.
Estimator is like a definition.
Estimator is the like, what are you going to use to estimate one of those things? So like, are you going to use a sample proportion? Are you going to use a sample mean? Are you going to? So basically, you look at the problem and go, well, which one am I trying to estimate?
Like the big picture, and then that's
And then this is the actual number. Yes. All right, cool. So let's look at an example.
I'm a bit of an ESL teacher.
Dr. Pearson is interested in the sleep habits of McKinney Boyd High School students. She selects a random sample of 10 students and asks them to record the number of hours they slept last night. Here are the results. We need to identify the point estimator, T-O-R, that we would use to estimate the parameter. And then we need to calculate the point estimate for each of those things. So, it is recommended that high schools... It is recommended that high school students get 8 hours or more of sleep each night. So Dr. Pearson wants to estimate the proportion P of all students at McKinney Boyd High School who got the recommended amount of sleeping time. What is the point estimator that we need to use to estimate P? Very good. P hat estimates P. So that's the point estimator. Now, what is the value of that? So what is the actual number? So p hat would equal what?
But you said we couldn't know that.
We don't know p, but we can get
Oh,
the
wait.
sample
Yeah,
proportion,
right.
which estimates p. So, what is the p hat for this problem? So, in the sample of 10 students, what is the proportion, the p hat, that got 8 or more hours of sleep?
1/5.
Say again?
1/5.
How'd you get that?
Because you go from 8 to 10, and that's just 2.
All right, there's 2 out of the 10, which is 1/5, which would be 20%, 0.2. That is the point estimate, ATE, okay? P hat is the point estimator, TOR. All right, Dr. Pearson wants to estimate the mean amount of sleep, mu, that students got last night. So what point estimator are we going to use to estimate mu? Perfect, you got it. X bar estimates mu. So we need to know the point estimate, the actual value of X bar. So we have to calculate the mean of these 10 numbers. How are you going to calculate the mean of these 10 numbers?
Divide them by the 10.
Add them all up and divide by
I'm
10.
already telling you that the average is less than 10.
You think the average is less than 10?
I think so.
I think you're probably right.
No way.
I would think it's probably somewhere around 5, 6, or
I think I'm about
7-ish.
70% sure of that.
Where'd you get 6.6?
Terrible.
Fantastic. Perfect. All right. But Dr. Pearson wants to go one step further and investigate the variability in the sleep times by estimating the population standard deviation sigma. So what point estimator would we use to estimate sigma? Very good. S sub x estimates sigma. Perfect. Now, we have to calculate S sub x. Does anyone remember how to do that?
I actually don't.
L1 and L2.
We only need L1.
Oh.
No, we don't really need L2.
But like that, you know
But
what I mean?
don't you have to put like a second column? Or
That
like
you only have to use L2 if you have probabilities associated with each number. But we don't.
Wasn't there like a question setting you would
Under stat calc 1 for one variable
Mrs.
stats.
Flick, how would we do this without a calculator?
You would have to use the standard deviation formula.
What might be that?
So we use our calculator, stat calc 1, and we get our standard deviation. What is it? 1.696? Perfect. That is the standard deviation. Now, again, I want to be very clear, and I will probably never talk about it again, so I hope you got it. The point estimator, TOR, is just this notation, p hat. P hat is the point estimator for this problem. X bar is the point estimator for part B, and S sub x is the point estimator for part C. Why am I telling you this?
Because there's a difference.
Because there's a difference. And when you take your next test or quiz or whatever, and you read a problem and there's no numbers given to you, and you are asked for the point estimator, you should not be shocked that you have no numbers. Because I'm not asking you for a number in that situation. If I'm asking only for the point estimator, you need to look and see which one of these am I trying to estimate, and that tells you which one of these estimators you're using. Yes?
Can they flip?
Nope. Nope. I can never do p hat is from you or what. No. It's always the same. No. Nope. I'm never trying to estimate a sample value with a population value. That's just weird.
So for in Sigma, there's the hours.
Uh-huh.
There's nothing for the
Correct, because that's just a proportion or a percent. So it's 20% or 0.2. So you don't have to have a units for P. Perfect. All right, cool. Moving right along. All right, back to our beads.
If you want to.
Do you guys think that you actually guessed the right proportion that was in here?
I know I did. I know that I did.
Yes, I did.
Is there any way that we as a class could get close to the value?
We've done it. We've done it. We've prayed.
We could average
Man,
every set of
like each row.
possible combinations. Here's what I mean by this. I could take Aaron and Colin's guess and average them together and put a little p hat on a dot plot. And I could take Aaron and Cole's and put their little p hat average. And then I could take the three of theirs and average them together and put a p hat. And then I could add in Mark's. And then I could take these four and add in Gabby's and now get another p hat. And guess what I'm building when I do that?
An average.
A sampling distribution of p hats. So basically, if I take every two of you, okay? So I take Aaron's guess and average it with every single person. I'm already gonna have 30 p hats, right? Because Aaron's with everybody else. Then I take Colin's and average it with everybody. So now I got 30 more p hats, right? And eventually we have built ourselves a sampling distribution of p hat, which should estimate the true p.
Okay, but what if we were all like really dumb? It's like,
Oh, I love that you asked me that question. What if some of your guesses were off for some reason? Well,
Like outliers.
we're averaging them out with all of the other people. So yeah, maybe, let's just say Aaron, for example, is colorblind. And he can't tell the difference between the red and the blue. Then guess what? All of Aaron's guess is bias. And any average, any p hat that Aaron is a part of is maybe going to be off a little bit. And so we're going to have that. But eventually Aaron's,
so many Aarons will just make it right.
it will average out eventually and will fix itself.
it's like, is it like the 30? Wait, does the 30 thing still apply here then?
Yes. No. Okay. Time out. This would not be the sample size being bigger than 30 because this is not a means problem. So we would have to do large count for this. N times P and N times 1 minus P. But as long as we have enough of those P hats, we would be having a normal
That's just
distribution.
so weird to me.
And we would be averaging out your color blindness.
But like, what if everybody's doing it?
Well, now we have a big problem, and we'll talk about that in a minute.
Oh, we will.
All right. So, confidence intervals. They are all constructed in the same exact way. We take our point estimate, that's the value, that's the number, plus or minus this thing called the margin of error. You heard of this, huh? You've heard of this. All right. So, guys, this is exactly what you did a few minutes ago. Your best guess was your point estimate. Okay, that was what you guessed it to be. That was what your value was for the p hat that was your sample. I gave you the margin of error. So when I said go 5% in either direction, that was a margin of error, 5% in either direction. So what you did was you took the point estimate, you added the margin of error, that gave you a high estimate for your interval. You subtracted the margin of error, that gave you a low estimate for your interval. And then you just put those into parentheses, and that was your interval. This is how you construct a confidence interval. Now, you then attach to this confidence interval how confident you are that you have captured the true value of the population. Once you say how confident you are that you have captured the true value, then you have created a confidence interval with a certain level of confidence. There is mathematical formula that goes with how to figure out how confident you should be. There is a mathematical formula that goes with what your margin of error is, but we won't talk about that until 8.2.
Come on now, Miss. Like,
Okay.
now you got me careful.
What if,
No,
like,
Miss
what if
Vicky,
your
don't
guess
erase
is, like,
it, please.
totally off the beginning?
But like the truth.
Sometimes your guess can be totally off because of issues like bias. Or think about this. What if when I had filled this, I had poured in the blue on one side and the red on the other, and I walked around with the red up against my hand, and I just showed you guys the blue side. Okay.
Well, that would be cheap.
That would be bias. And all of your guesses would be off because of that bias.
Not mine.
Can that margin of error overcome that bias?
This is a
Would that not be a form?
Because if I did that and all of your guesses really sucked, and I gave you a 5% window outside of a guess that was really bad because I only showed you the blue side, does that margin of error overcome that?
I does not.
No.
Not likely.
Margin of error can't overcome bias.
Would that
The
be?
margin of error can't overcome the fact that Aaron can't see red versus blue.
That's true.
He still can't see red versus blue. He looks at this and goes, oh, there's 0% red in there. I don't see no red.
I know.
Margin of error can't overcome that.
It's just for the
The margin of error overcomes something called sampling variability. It overcomes the fact that all of you had a slightly different guess. That's what margin of error does.
That's like
Okay?
the response bias because they
Last thing I want you guys to write down.
ain't showing.
That is like response bias. You're absolutely correct. All right, here's the last thing I want you guys to write down, and then we'll call it a day. The point estimate. The point estimate will always be the exact middle of the interval. When you guys were doing your guess, you gave your guess, and then every single interval you created, the very exact middle of that interval was your guess. Because you were always adding and subtracting the margin of error from your guess. Okay? And that will always be true. Got it? Perfect. So what is this margin of error we speak of? Margin of error describes how far, at most, we expect the estimate to vary from the true parameter. Yesterday, you guys had the opportunity to guess the population proportion of red beads in the jar. And you were given some margin of errors that you were able to be within. I gave you 3 different ones: a 5%, 10, or I don't remember, 20%, and 30 something. Anyway, it doesn't matter. But anyways, those margin of errors. So when you did that first one, it was 5% on either side that you could go from your guess. That was, I expected you to be at most 5% off from the truth if your guess was really a good guess. But then I realized, you know what? I didn't give you a lot of information about what was in here. Also, I didn't really show everybody the same amount of time. I didn't turn it the same amount of time. So maybe it was a slightly biased. So I gave you a little bit bigger of a margin of error because we I expected you to vary a little further, thinking through all of those things. That's what margin of error tells us. Here's what margin of error does not tell us. Margin of error does not account for any source of bias. You got it. So, again, I believe yesterday we talked about Aaron being colorblind, right? So, if Aaron is colorblind, then me allowing him a 5% margin of error really doesn't help him. It doesn't change the fact that he's got a biased guess because of the fact that he's colorblind. If I had walked around and only shown you the blue and kind of hidden the red, right? If I had done half and half like that, then giving you a 5 or 10 or 20% margin of error doesn't change the fact that I biased you by hiding something.
It'll still make it more probable.
Yes, now, by giving you a little bit of wiggle room, I'm giving you a better chance of getting it right, but it doesn't take away the bias that is there because of the fact that I messed with you if I had done that.
The more wiggle room you give, the less useful it is.
The more wiggle room, the less useful, yeah.
So the margin of error is just like the percent that like we're.
We need to find a
Yep.
healthy balance.
We need a healthy balance of a good, accurate estimate.
Like that Michelle Obama food parody.
Yes, a good, accurate estimate, but not too much wiggle room. All right, now, sometimes we want to decrease our margin of error. So this is in the event that our margin of error is maybe a little too wide and we've got a really big, wide interval. It's not really that useful. I want to decrease that margin of error. I want to decrease the width of that interval. Here's how we can do that. The first way is we would have to decrease our confidence level. Think about it. When you guys were 99 or 95% sure that you had captured the true proportion of red beads in this jar, you had a pretty wide interval going on, right? Like a 60% window. And when you had a smaller window, you were less confident that you had gotten it right. So if my margin of error shrinks, I'm getting a little less confident. That's one way you can decrease how wide your interval is. Colin.
Are we trying to get the smallest margin error with like the highest confident? Okay, I got you.
Yes, we're trying to get the smallest margin of error with the highest amount of confidence, okay? So let's say we're like, you know what? I'm already at only a 90% confident. I don't want to change my confidence. So how can I shrink my margin of error but keep the same confidence level? Here's another way you can decrease that margin of error. Increase your sample size. If you take a bigger sample from the population, you should have a better idea of what the true value is, and then you can shrink that margin of error.
Basically, in all contexts, always increase sample size.
Yes. How to fix anything that you do, statistically speaking, increase your sample size. All right, and then the last thing about margin of error that I want to make sure we've actually already said this. Lainey kind of gave us this answer. The margin of error is a measure of variability, similar to standard deviation. Margin of error is a measure of variability similar to standard deviation. Again, it's the wiggle room. It's how much your guess can vary and still be right. So it is a measure of variability. So this should help put sense to how do I decrease standard deviation? How do I decrease variability? I increase sample size. It all goes together.
Done.